Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 8, Lesson 5 on working with multiple transformations. In this unit so far we've seen a lot of different transformations that can be done to functions. We've seen shifting, vertical and horizontal stretching. We've seen reflection over both the x and the y axes. Today we're going to try to put a lot of those together to transform a function, a parent function, in multiple ways. So let's jump right into it. Here we go. Working with multiple transformations. Many times more than one transformation will occur to a parent function to produce a different function. It's important to be able to identify what transformations have occurred and how to produce them algebraically. So let's take a look in exercise 1 at how this is done. A function f of x is shown graphed. The function g of x is defined by g of x equals 3 times f of 1/2 x. Letter A. Using its definition, find the value of g of -2. State the point this corresponds to on the graph of g of x. All right, so what I'd like you to do is go ahead and just use this definition and the graph of f to evaluate g of -2. Pause the video and go ahead and try that right now. All right, let's take a look. So, anytime we have a formula for a function, it's worthwhile if we're trying to evaluate the function to use the formula. So g of -2 is going to be 3 times f of 1/2 times -2, which is 3 times f of -1. Now, to figure out what f of -1 is, we've done that many of times, we come over to the graph and note that the point -1, 3 lies on the graph, so f of -1 is equal to 3. So g of -2 is 3 times 3, and that gives me 9. Now that means that the point -2, 9 lies on the graph of g of x. But even more to the point, what that means is that the point -1, 3, that particular point on the graph of f of x really got transformed into the point -2, 9. That's where that point got mapped to through these transformations. And that gives us a key to letter B. Based on A, what two transformations must occur to the graph of f of x to produce the graph of g of x? In this case, does the order matter? All right, so pause the video now and see if you can tell me what two transformations are occurring to the graph of f of x in order to produce the graph of g of x. Take a moment to think about that. All right, so we can do it even without really kind of thinking about the point -1, 3, although again, it's kind of helpful. The first thing I can note is that I'm multiplying the x variable by 1/2 right before I do anything else. Now that is a horizontal stretch by a factor of 1 over 1/2, or a horizontal stretch by a factor of 2, right? So we're getting a horizontal stretch by a factor, that looks like stretch by a factor of 2. And number 2, right, because we're multiplying the overall function f of x by 3, let me see if I can point at the 3, because we're doing that, we're getting a vertical stretch by a factor of 3. So let's write that one down as well. A vertical stretch by a factor of 3. Now, we can really see both of those if we think about the point -1, 3 getting mapped to the point -2, 9, right? The -1 got multiplied by 2, that became -2. The 3 got multiplied by 3, and that became 9. The cool thing is we can really look at these in either order. Now I wrote them down as the horizontal stretch first, because really truly when x goes into the function, it first gets multiplied by 1/2, then the function gets sort of operated on that input, and then we multiply by 3. But the real key, does the order matter? Not in this case. So no. Oftentimes the order does matter in multiple transformations, but it doesn't in this case because we can certainly stretch this function first by a factor of 3 vertically and then expand it horizontally by a factor of 2. All right, let's kind of keep going on this. Letter C. Below, show how other important points on the graph of f of x are mapped based on b, and then plot the graph of g of x. Now, you might think to yourself, what do you mean by other important points? Well, think about it for a second. If I really want to produce the graph of g, I've got to get probably where this point goes, this point, which I just did, this point, and this point. If I can figure out where those 4 points go, then I can really get a good graph of g. So why don't you go ahead and use those two things. And here, this is the way I would think about it, right? Like if I take that point -1, 3, and let's say I stretch it first in the horizontal direction, and then I stretch it in the vertical direction, it kind of looks something like that. You know, -1, 3, then becomes -2, 3, and then it becomes -2, 9. Go ahead and do that actually with this point, and that point to figure out where they all go, and then try to plot g of x. All right, well, let's take a look. Here we've got the point -4, 0. If I first stretch that in the horizontal direction by a factor of 2, I get -8, 0. And then if I multiply the y-coordinate by 3, I still get -8, 0. Remember, a vertical stretch or compression will not change a 0 of the function. Now I also have the point 1, -3. If I stretch that by a factor of 2 in the x direction, I have 2, -3. And then if I stretch it by a factor of 3 in the y direction, I have 2, -9. And finally, if I take that point 4, 0, stretch it by a factor of 2 in the x direction, then stretch it by a factor of 3 in the y direction. Again, that doesn't change the y-coordinate because 0 times 3 continues to be 0. The great thing now is if I plot those 4 points and connect them with straight line segments, I now get my graph of g of x. A graph that has both been stretched horizontally by a factor of 2 and stretched vertically by a factor of 3. Keep in mind what we talked about in our lesson on horizontal stretching and compressing. That factor in there, it's always the reciprocal of that that gives us our factor, right? So if I take 1/2 and I flip it, if you will, to get 2/1, I can see that I'm stretching it by a factor of 2. Okay, so multiple transformations, both a vertical and a horizontal dilation. Exercise number 2. On the graph below are 2 functions. It's known that f of x equals 16 minus x squared. The function g of x is both a vertical stretch and a horizontal compression of the function f of x, and is defined by g of x equals a times f of b of x. All right, now before we kind of get into this problem, this is sort of almost the mirror image of the one that we just did. We have the 2 similar transformations, right? Except here, we don't know the values of a and b. That's what we're really going to be playing around with in the problem. So let's take a look at letter A. Based on the 2 maximum values, what must be the value of a in simplest form? All right, so in other words, a is the number that's really kind of helping us think about the vertical stretch in this particular problem. And I can really get at that by saying, well, look, the maximum value of f of x occurs here, and g of x occurs here. See if you can then figure out what the value of a is based on that. All right, well, what I definitely know is I know that g maximum is 20 and f maximum is equal to 16. I can now basically say, well, then that means that 20 is equal to 16 times a, and a is equal to 20 divided by 16. I could reduce both of those by a factor of 4, and I'll get a is equal to 5/4. If you really like it better as a decimal, you could also say that a was equal to 1.25. Either one is fine, depending on whether you like fractions better or decimals better? Letter B. Based on the location of the zeros of both functions, what must be the value of b? Now keep in mind, right, what we're doing is we're taking the blue graph, that's f of x, and we're horizontally compressing it to get the red graph, g of x. So take a look at the zeros, right, of f of x and the zeros of g of x, and think about what factor you would need to compress those by in order to kind of think about the value of b. Pause the video now and see what you can get. All right, well, we have zeros originally, so think about this. We've got f of x has zeros at x equals negative 4 and positive 4. G of x has zeros at x equals negative 1 and positive 1. So we're compressing by a factor of 1/4, but that means, and this is where it's tricky, b is actually equal to 4, right? Seems like b should be 1/4, right? But if b is 1/4, then we'd in fact be stretching the graph of f of x out by a factor of 4. Since we're compressing all of these zeros by a factor of 1/4, then that leads us to b being the reciprocal of 1/4, which is just equal to 4. All right, so we know a and b, right? A is 5/4 or 1.25. B is a nicer number, it's equal to 4. Let's take a look at letter C. Determine an equation for g of x in terms of x by using the values of a and b that you found. Write in simplest form and verify using your calculator. All right, this is kind of cool, and the algebra is a little bit challenging, but I'd like to see if you can do it on your own, and then we'll take a look at it and verify that we actually have the right formula by producing this graph again. Pause the video now and see if you can come up with a formula for g of x. All right, well first, let's write this thing down, but with the proper values of a and b. All right, so g of x is going to be 5/4 times f of 4x. Excellent. Now we just have to kind of substitute. G of x is going to be 5/4 times 16 minus 4x squared, right? So wherever there's an x in f of x, I now need to put a 4x in. All we're doing there is composition of functions. Now I can do a little bit of work here, right? So 4x squared is 4x times 4x, or 16x squared. And maybe to make this look really nice, I can distribute. 5/4 times 16 is actually equal to 20. And of course, the 5/4 is going to distribute through both of them. And I get a very nice final formula for g of x. G of x is 20 minus 20x squared. Now, if I've done everything correctly, determined the value of a correctly, b correctly, I've then used them to figure out the formula for g of x, I can see if this is correct using my graphing calculator. Now, got a little bit ahead here, all right? I've already, in my graphing calculator, put in f of x. F of x is equal to 16x squared. I've also adjusted the window so that it goes from -5 to 5 along the x-axis and -5 to 20 along the y-axis. And that's exactly what we've got sort of in this particular image. So now, let's throw in our g of x. I'm going to go into Menu, Graph Entry Edit, Function, F2, it's all ready for me. 20 minus 20x squared. And there it is. It's even the right color, right? So it's kind of nice. You know, we can see, yeah, we got the right values of a and b because now our graph matches what we were looking for. Excellent. All right, let's kind of keep playing around with this, see what else we can do with multiple transformations. Because so far, all we've worked with now are a combination of a vertical and a horizontal stretch or compression. Let's take a look where we mix a few different ones together other than those. Exercise number 3. The function f of x equals x squared is shown graph below, along with another quadratic function g of x that has the general form g of x equals a times x plus h quantity squared. Letter A. What two types of transformations must occur to the graph of f of x to create the graph of g of x? Now, you can tell this basically by just looking at the form of this equation, right? F of x is x squared, g of x is a times x plus h quantity squared. So, what two types of transformations have occurred? Don't worry about like how much or anything like that. Just tell me the two types of transformations. Well, we've definitely had a horizontal shift, right? The x plus h does that. So this is a horizontal shift. Now, what might be a little bit more challenging is exactly what the a is doing. Now, we know that if we multiply the overall function by a constant, we're either going to get a vertical stretch or we're going to get a vertical compression, right? That's where it takes a little bit to sort of look at the original graph in blue and then the new graph here in red. And I know on your worksheet they're both black, but we're looking at f of x, we're looking at g of x. Now notice on this original parabola, right, we have this turning point, 0, 0, and then to go to the next point, we go over 1 and up 1, right? And then to go to the next point, we go over 1 and up 3. When we look at this graph, right, what's happening is we go over 1 and up a half, over 1 and up 1.5, right? So what's happening, right, is we're definitely getting a vertical compression. We're taking this graph and we're kind of smushing it on down. That's a technical term, smushing. We're smushing it on down. We're compressing it. So we have a vertical compression. All right. So now in B, let's get to the heart of it. What are the values of h and a? All right. I'd like you to pause for a moment and see if you can think about what the values are of both h and a. Okay. Well, a little bit unfortunate here, but since I'm moving the graph of f of x to the right 5 units, I really need to subtract 5 from x in order to do that, okay? So what I have to say is that h is going to be equal to -5, right? We're moving that graph 5 units to the right, which means most of the time I want to think about that as subtracting 5, but the way that the problem is phrased, I'm going to be adding a -5. Now we already kind of got at what a was, right? And it's really kind of easy to think about it as if I go over there, one unit across, 1 unit to the right, I move 1 unit up. But here, when I move 1 unit to the right, I move a half a unit up. Or maybe it's even easier to think of it this way. If I moved 2 units to the right, I would go 4 units up. Here, if I moved 2 units to the right, I'd only go 2 units up. So what clearly is the case here is that my vertical compression is by a factor of 1/2. Remember, vertical stretching and compressing works exactly the way you want it to, right? In other words, if I vertically compress the thing by a factor of 1/2, well, then the a value is 1/2. It's those horizontal ones that are kind of counterintuitive like that. Okay. Very similar to before, let's take a look at letter C. Write an equation for g of x. Use your calculator to verify. Well, this is far simpler. The last one we had to do some algebra on. This one's a piece of cake, right? All I literally want to do here is write that formula. Now, you could totally multiply x minus 5 out, x minus 5 times x minus 5, etc. But there really is no reason to do that. In fact, let's take a look at the graph really quick. All right. This one I didn't get a head start on, unfortunately. Actually, maybe just put in a new page. Let's add a graph. It's F3. Actually, I'll just do a brand new file. Forgot that was going to happen. So let's do this. Let's put in that original parabola, x squared, All right, and then we'll put in our g of x, and that's going to be 1/2 or 0.5, whichever way you prefer it, times x minus 5 squared. And maybe I'll even, set my window the way that I want it. That's -5 to 10. Let's do that, -5, just to make sure it looks the way it does here, -2 to 10, and there we have it, right? This graph that has been shifted 5 units to the right and sort of smooshed down vertically. Now, it would be very understandable if you said to yourself, well, it really looks like the graph has been sort of horizontally stretched wider. And it can be looked that way, right? It really can be. It's trickier to deal with because then what's going to be happening is you're going to have to be multiplying that x inside there by some constant. And that gets to be a lot trickier here. But parabolas especially, for whatever reason, when we vertically compress them or vertically stretch them, it also appears to make their width different, right? This width looks like it's actually quite a bit wider. And if we hadn't ever sort of like shifted it, it certainly would sort of be wider in that sense. So you could look at it as either a horizontal dilation or horizontal stretch or a vertical compression, either one. In this case, it's easier to deal with it as a vertical compression. All right, let's take a look at one that I love. Exercise number 4. An egg shape is modeled using an upper portion that is a semicircle whose equation is f of x equals the square root of 36 minus x squared. The lower portion is to be modeled using the function g of x, which is a transformation of the function f of x. Describe the transformations that would need to occur to the graph of f of x to produce the graph of g of x, and give an equation for g of x. Graph on your calculator to verify. All right, so here, all we're giving you is the equation of that upper curve. And we're saying this one is a series of a couple transformations of this one. What are they, right? And then once you've identified them, then what we want to do is we want to figure out an equation for g of x to give us this overall egg-like shape. Pause the video now and play around with this. All right, well, one thing I know for certain is that I've certainly taken this semicircle and I've reflected it across the x-axis. There's no doubt about that. So I'm going to write that down. I have a reflection across the x-axis. Now, keep in mind that when I reflect across the x-axis, that's going to be pretty easy. All I'm looking to do is multiply the entire function by -1. Now, if I did that and did that alone, all I would end up doing is getting sort of the other half of the semicircle. I'd just get something like that. So that, I mean, very poorly drawn, but I would get something like that. Now, the question is, how do I take that and create, right, the graph that's in red? Now notice, right, what's not changing are those x-intercepts. And the thing that won't change the x-intercepts, the zeros, will be a vertical stretch, right? It will be a vertical stretch. Now, right now, right, this thing has a peak value 6 units away from the x-axis. This one has a peak value, I guess, or minimum value, 10 units away from the x-axis. So what I know as well is that I'm going to do a vertical stretch. And I can think about the factor by just basically taking this value and dividing it by this value, right? Now again, I'm thinking about that sort of 10 divided by 6, which gives me a factor of 5/3. Okay? So how do I make both of those happen at the same time? Well, I want to multiply the overall function by -1. That'll give me a reflection across the x-axis. And then I want to multiply that by 5/3. I can do both of those at the same time by simply multiplying all the values of the original function by -5/3. Now again, you can really think about it as sort of saying, well, g of x will be equal to, that's beautiful, g of x will be equal to 5/3 times -1 times f of x, right? Where the -1 is giving me the reflection across the x-axis, and the multiplying by 5/3 is then stretching that lower semicircle out so that instead of having sort of a minimum value here at -6, it has a minimum value down there at -10. Ultimately though, right, what that gives me when I multiply those two together is -5/3. And then I'm just going to throw in the equation for f of x, and that's 36 minus x squared. So there's our formula for g of x. Let's take a look at our egg shape. All right. Let me bail out of here, and yet again, I'm going to open up a brand new document. I'm going to add a graph. Might as well put in that first semicircle, which is, I'm sorry, not 16, but 36 minus x squared. That's kind of cool. We'll get the window in just a second. Whoops, no. I can now get this, which is going to be -5/3 times the square root of 36 minus x squared. There's that one. Looks like I'm going -10 to 10. That's all good. It's more of the y values that I want. -12 to 12. And boy, that looks funny, doesn't it? You know, it certainly doesn't look exactly like this. And the reason why, I'm always kind of surprised and shocked when I see that. The reason why this doesn't look precisely like this is that the screen itself is not what's known as square, meaning that there's a different scale along the y-axis than there is along the x-axis. And that's a little bit unfortunate because it sure doesn't look like the beautiful egg shape that I was expecting. Now, if you go into menu and you go into window, there is something that is hopefully, here it is. Uh-oh, nope. Something called zoom square. Now, if this works the way I think it's going to work, I'm going to hit enter. And then what zoom square does is it ensures that the scale along the y-axis is the same size as the scale along the x-axis. And that pretty much gets the job done, but then loses the bottom portion of my egg, and so I still don't really have what I want it to look like. I'm going to try to do zoom out and just hope. Yeah, there we go. And then I zoomed out again. So I end up getting an exceptionally tiny egg on the screen. I'm just going to give up on this. Anyway, I think we've more or less verified it's correct. And if not, I don't want to keep torturing you with apparently my lack of good window management. All right, let's do an easy one that thankfully does not involve me going to the graphing calculator. Exercise number 5. A quadratic function h of x has a vertex at the point -6, 12. The function k of x is defined by the equation k of x equals 1/4 h of x minus 8 plus 10. Then if the function, then where will k of x have a vertex point? Explain how you arrived at your answer. Fantastic. So what I'd like you to do is I'd like you to pause the video. I'd like you to look at the definition of k of x and ask yourself, what transformations have occurred to the function h of x to produce k of x? And then basically take those transformations and do them to this vertex point. Pause the video now and see what you get. All right, well, I'm going to really work sort of my order of operations. So when I look at this definition, I see that I'm subtracting 8 from the x to begin. So the first thing I know that's going to happen, and this is really kind of going at explain how you arrived at your answer, we're going to kind of do that and then we're going to get our answer. So the first thing I notice is that I have a right shift of 8 units. Now what's kind of cool is I can literally say, well, that's going to take -6, 12, and it's going to map it to 2, 12, right? It's just going to scoot it 8 units to the right, so I just end up adding 8 to -6, and I'm now at 212. That's not my final resting place, right? So then the second thing that's happening is that I'm multiplying the overall function by 1/4, and that's going to be a vertical compression by 1/4. Now, what's that going to do? Well, that's going to take my point at 2, 12, and it's going to make it into 2, 3, right? I'm going to take my y value at 12, and I'm going to multiply it by 1/4, i.e. I'm going to divide it by 4. And now, 2, 12 becomes 2, 3. The final thing that happens is that I add 10 to the overall function. And whoops, and that's going to be a vertical shift up by 10 units. And that's going to take 2, 3, and it's going to end up with my final answer, 2, 13. And there we have it. All right. And that's really kind of looking at a formula and being able to identify the different transformations that have occurred based on that formula. All right, let's wrap this up. Thankfully, we have many more types of functions that we're going to be looking at throughout this course. And now that we have all of our fundamental transformation tools, we can now start to look at those as we sort of investigate new functions. So we're going to get to see shifting and reflections and horizontal and vertical dilations throughout this course, right? Or at least throughout the remainder of this course on new function types that we explore. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.